Okay, get excited, because in this video we're going to get to see one of the all-time great theorems, and it is called Euler's formula in the plane. Now, there's an Euler's formula in other spaces as well. We'll see it for the plane, and in particular, we'll see how it relates to planar graphs. So let's jump in. The starting point, in a way, is asking questions about counting, like how many blank are there in a certain kind of graph? Like, how many vertices, how many edges can there be? And we know if there's n vertices, then there can be at most n choose 2 edges. So n choose 2, remember this is like n squared. It's n times n minus 1 divided by 2. It's the number of pairs of distinct elements you can have in an n-element set. So that's like a quadratic number of edges, quadratic in the number of vertices. But what if the graph is planar? Is this still true? Can you still have a quadratic number of edges in a planar graph? Let's see. That's a question we're going to answer today in this video. Also, when we talk about embedding a graph, we have all these choices, right? There are many different continuous maps from a graph into a space, assuming there are any. So in this case, if it's a planar graph, there's some embedding into the plane, but there's a bunch of different ways we can do it. So we have all these choices. And when you have all these different options, you can still ask, like, what is invariant about the faces? Now, when I say there are different faces, remember the faces are those connected components of the graph or the plane minus the embedding of the graph. So it might seem like the faces are just completely dependent on the embedding, but there's some aspects to the faces that are going to be invariant to, in fact, show up in any embedding. And we'll see some of those examples as well. All right. So, but to warm us up, I'm going to talk about two different invariants. Now, these are very, very simple invariants. We could have done this on the first day we covered graph invariants. And they look like kind of the same. Okay, so on the left here, I have one that's the number of vertices plus the number of edges. And you know that the number of vertices is a graph invariant, the number of edges is a graph invariant, so their sum must also be a graph invariant. And on the other side, I've got the difference. Okay, so they're both clearly graph invariants, but they behave differently. So here's the simplest example that highlights the difference. You see, I've got this edge. This is a graph with one edge, 2 vertices. So 2 plus 1 equals 3, which is not equal to what I have over here, which is 3 plus 2, which is 5. So these two graphs are distinguished by this invariant. Seems like a good thing. On the other hand, over here, this graph has 2 vertices and 1 edge again, so 2 minus 1 is equal to 1. And here I have 3 vertices and 2 edges, so it's actually equal to 3 minus 2. Okay, so this invariant doesn't distinguish between these two cases. Now, generally, that would be kind of a bad thing because it says, well, somehow this invariant doesn't give us as much information. It doesn't, at least in this particular case, for these two graphs, this invariant distinguishes them and this one doesn't. On the other hand, this invariant came from thinking about what happens when we subdivide an edge. And we saw that, in fact, these two graphs were topologically equivalent. That is, they were homeomorphic graphs. Their geometric realizations were homeomorphic topological spaces. And so, in general, whenever you take a graph and you subdivide an edge, you're not going to change this invariant. So this is invariant to subdivision. And really, this is getting us towards a topological invariant. So let's give this thing a name, this invariant. I'm just going to call it E of G for now. E is for Euler. Usually it would be called the Euler characteristic, and it would be denoted with Greek letter chi. But for graphs, you have to be careful because chi is the chromatic number. It's the number of colors you can use to color the vertex set of a graph, so you can't you can't use it for both things. So let's just call this E of G for now. And I claim that this is in fact a topological invariant. Now, topological invariance is just like graph invariance, is that if you have equivalence in topology, then the invariance should come out the same. In other words, for two graphs, if I have the geometric realization of G and the geometric realization of H, if they're topologically equivalent, homeomorphic, then it should be the case that E of G is equal to E of H. So this is a invariant on graphs, but it also captures some aspect of the topology. So let's do some examples. How about cycles? So a cycle, let's say I have a cycle that has, oops, this is supposed to be a C. Is there any hope for changing this into a C sub A? This is a cycle with A edges. This, of course, is homeomorphic to the geometric realization of a cycle with B edges for any A and B, as long as A and B are at least 3 here, because all the cycles are homeomorphic to a circle, so they're homeomorphic to each other. And in this case, it's easy to check that this invariant on the cycle, because cycles have the same number of vertices and edges, the difference is 0, so it's also equal to E of CB. Okay, so this simple case you can check. Another very interesting case is the case of trees. If I have a tree T, then it has, let's say it has n vertices, and I subtract off the number of edges. The number of edges in a tree is n minus 1. So n minus 1 is plus 1. The whole thing is plus 1. Okay, so for any tree, this invariant comes out to 1. And actually, we saw one example of this, of course, because a path is a tree. We saw that came out to 1. But it's actually true for any tree. And maybe to get our head around this invariant just a little more, let's do an exercise. So let's let G be connected. This is really important. A connected graph. Then I claim that E of G is equal to 1 if and only if G is a tree. Let's check if this is true. One direction, we've already done. We've already saw that if G is a tree, then E of G is equal to 1. Now we want to show the other way around, that the converse also holds. So if we have E of G equal to 1, then we know it has exactly n minus 1 edges. And we're going to show that a connected graph with n minus 1 edges is a tree. And one way to work that out is to just remember this fact about the number of edges being half the sum of the degrees. Well, half the sum of the degrees is n minus 1. That means that the average degree, which would be 1 over n times the sum of the degrees, that's how you compute an average, would be 2 minus 2 over n, right? Because I've moved the 1/2 over and I divide by n. So I got 2n minus 2 divided by n, which is strictly less than 2. Okay, so if the average is less than 2, then some vertex has degree 1. Now, it couldn't have degree 0, because if you have some degree 0 vertices, then the graph is not connected. Okay, so a degree 1 vertex, that's a leaf. And so now you can finish this proof on your own now because you know everything you need to know. You know that if you just prove that G is a tree, you could do it by induction, right? And the induction would just be by removing this one leaf. The result removes one vertex, one edge. E of G minus this leaf is still 1. So that's a tree. And then you've just added a leaf onto a tree. It continues to be a tree. One thing, maybe I'll just highlight this as an example of why you really need to be careful about the graph being connected. I could have had a graph like this, which is not connected. But if I look at this invariant, I get 1, 2, 3, 4, 5 vertices, 4 edges. This is 1, but it's not connected. So it's not a tree, but it's also not connected. So connectivity matters here. But this is just about vertices and edges right now. What about the faces? So once you draw the graph in the plane, you have an embedding of the graph, then you have this notion of faces. So you've got the zero-dimensional structure, that is the vertices. You've got one-dimensional things, these edges. And now you also have these two-dimensional things, which are faces. And somehow those should play a role. And I told you in the beginning that really part of our goal in talking about Euler's formula in the plane is to start asking counting questions about the faces. So let's let this G, this underline G, be an embedding of some graph G. So what I mean here, of course, is that there's some embedding of the graph G into the plane, and this is just the image of that embedding. We're going to sometimes talk about this as if it's a graph, and when I talk about the edges of the embedding, I'm really referring to the embeddings of those edges. So they're going to be paths in the plane. Okay, and our key idea that's going to drive all of this is this idea that when you split a face, that is, if you add an edge that cuts across a face, that this is going to be analogous to that case of subdividing an edge. And what I mean by that is if I add this edge that cuts a face into two, I've added one edge and I've also added one face. So if I wanted to keep something invariant, I would need to have this subtraction between edges and faces. That is, if I go plus one edges, I should go minus one face, or if I go plus one face, I should go minus one on the edges. If that's not so clear, let me actually write out. So one thing you might try is some kind of invariant. Well, I don't have a name for it. We don't really need a name for now because this isn't going to be the one we settle on. But something like an invariant for the embedding, which counts the number of vertices minus the number of edges, and then adds back in the number of faces. And I should be careful here because the faces really depend on the embedding. So I could put underlines here as well, but the vertices and edges, at least the counts, don't change. We will eventually find that the counts here don't matter, but that's really the conclusion and not the hypothesis we want to make. So something like this would have the right effect where I might expect that going from this graph to this one, I won't change this invariant because in this case the plus one to number of faces and one more edge will cancel out because this is positive and this is negative. All right. So let's try it. Let's see what happens. We can now state the main theorem which encodes Euler's formula. It's the following. The number of vertices minus the number of edges plus the number of faces is equal to 1 plus k. So this is for any planar graph with k connected components. This right here, this is Euler's formula in the plane. If you have other kinds of spaces that you're trying to embed your graphs in, you actually can end up with something different here on the right-hand side. Okay, so the key idea is to realize that only one of two things can happen when you add an edge. Either you reduce the number of components by 1, because two things which were not connected are now connected, so the two components became 1. Or you can split a face. And that face now becomes exactly two faces. Okay. Once you have this idea, then the proof is going to be relatively simple. to actually check that this holds, we're going to use the Jordan curve theorem. Okay, so the idea is, again, we're thinking about a single edge. And so here's an edge UV. And I claim that there's just two cases. If I look at a neighborhood of the edge, so I look in this little circle around a point on the edge, again on the embedding of the edge, I know that locally the edge splits that neighborhood into two pieces. If there was a path that connected the two pieces, then they were on the same face. And if I were to, say, remove that edge, then I could complete it into a Jordan curve, and U and V would be in separate components. Okay, so this is exactly the case where adding the edge from U to V now makes these two components 1. Okay, so this is adding 1 to the number of components, and the number of faces stays the same, because anything that was a face before is still a face, and this edge that I drew can't separate two faces because I have this other path. All right, and so we're using that same intuition that we used when we proved the Jordan curve theorem, that if you're in the neighborhood of an edge, then you can walk along the side of the edge, and there's only one face that you're on as you walk along one side of an edge. Okay. So the other case is that if there was not a path, then there was that edge is part of a curve which separates the two sides. Again, I'm looking at the neighborhood of a point on the edge. And so if that's the case, then there was a face here which are separated, and before I added that edge, they were connected, right? Because I can now find a path, even just in this neighborhood, that goes from one side to the other when this edge is not there. So in this case, adding the edge separates a face, what was a single face, into two faces. Okay, so those are exactly the only two cases, right? Whether or not the two sides of the neighborhood of the edge were connected or not. So if those are only two cases, we're going to do a little induction. The idea is to do induction on the number of edges. So the base case is when there's just no edges at all. In this case, there's only one face, right? Everything in the plane, other than the vertices, you can connect by a path. And the number of components is exactly n, 1 for each vertex. And so you can work it out now that the number of vertices minus the number of edges plus the number of faces is going to be equal to, well, we said this of course is n minus the number of edges, which is 0, plus the number of faces, which is 1, which turns out to be exactly k plus 1, because n is equal to k in that case. All right, so the base case works. And now we're going to go by induction. We're going to remove one edge. So now we have a subgraph, g prime, which is a subgraph of g. And there's two cases to consider. Remember, either the number of components is one more than it was before, or the number of faces is one less. Now, let's do them one at a time. So first, if the number of components went up and then the number of vertices and faces were unchanged, then P of g minus E plus F is equal to P of g prime minus E of g prime plus 1 plus the number of faces in the embedding g prime. Now, we said that these didn't change. So by induction, this graph, which is smaller, the v minus the e plus the f, is exactly 1 plus the number of components, which is k plus 1. And then this is going to be minus that 1. So this is 1 plus the k plus 1 minus 1, which is equal to k plus 1 as desired. Okay, so just working through the arithmetic, you see that in this case it holds. And we're just, again, using induction on this smaller graph G prime, which has fewer edges than G. Almost the same proof now in this other case where the number of faces has changed and everything else has remained unchanged. So VG minus EG plus FG. I'll try to be careful to underline these G's for now for this particular embedding, is equal to number of vertices in the new graph minus number of edges in the new graph, which of course is one fewer, and plus the number of faces now, which is F plus 1. Okay, so that's the one that has changed. You can cancel these, so the plus 1 here and the plus 1 here, they cancel, and the result is 1 plus k. So there you go. So this is it, right? Just by induction on the number of edges, we get the main theorem, again using the fact that there's only these two cases which came from the Jordan curve theorem. All right, so what are the consequences of this? It means that if you have a connected planar graph, every single embedding, no matter how you embed it in the plane, there's going to be 2 plus m minus n faces, right? M is the number of edges, n is the number of vertices. So there's always exactly this many faces. So you can't, even though you can change how you embed it, you can get different looking embeddings. You can get embeddings where the faces maybe have different edges, maybe even different numbers of edges on them. The number of faces is going to be the same. All right, so it's invariant. So it actually makes sense for us to write things like the number of faces in the graph, at least when I talk about the size of it, instead of always writing FG with the underline referring to a particular embedding. Okay, so it's independent of the embedding, which is great. Now, this is also like saying that it's actually the number of faces is a graph invariant for a planar graph. So this is often the way you see it written, where n, m, and f are vertices, edges, and faces, the number of vertices, edges, and faces. And for connected graphs, right, 1 plus the number of components is going to be 2. And this is maybe the most common way you see it written. And this is maybe the slightly more correct way, where k here is the number of components. And if you want to kind of wrangle this into a graph invariant, you kind of move the faces to one side, and you get that this 1 plus k minus n plus m, well, it's a graph invariant. We kind of knew that already because n and m are graph invariants, and the number of components is a graph invariant. But it's also a topological invariant. Okay, so these are this is maybe this other way of thinking about the Euler characteristic of a graph in terms of graph invariance and topological invariance. All right. So next time we will talk a little bit more about Euler's formula and some of its consequences. In particular, we'll see how to count things and put bounds on how many vertices and edges, faces there can be in a planar graph. And I think I promised it in this video, but it's actually going to show up in the next video, so stay tuned.